Now, in our previous lecture, we have discussed the properties of polynomial equations. We have defined the Sturm sequences and the Sturm's theorem, which gives us the exact number of real roots that lie in a given interval a b. We study the number of changes in the signs of the Sturm sequence. We take the difference between the number of changes in signs at 2 points a and b, then we decide upon the number of real roots that lie within that particular interval. So, what we are considering here is a polynomial equation p n x is of the form a naught x to the power of n plus a 1 x to the power of n minus 1 plus so on a n minus 1 into x plus a n with a naught not equal to 0. Now, if all the roots are real and distinct, so let us take the case of all roots xi 1, xi 2, xi n are real and distinct. Then I can always write this polynomial p n x as a product of the linear factors x minus xi 1 into x minus xi 2 so on x minus xi n. If the roots of some of them or all of them have multiplicity, we can extend this to the case of the multiple roots also. Therefore, a numerical method that we would wish to construct would try to extract a linear factor out of this set. Then we want the next root to be determined. We shall deflate this polynomial, that is divided by a particular root that has been extracted, and we then go to find the next root by using the method on the deflated polynomial. Now, if the roots are complex pair, let us say two roots are complex pair, let us take the case of two roots, say xi 1 xi 2 or a complex pair. So, let us take these roots as a plus minus I b. Then let us see what happens to this factor. So, I can write this as x minus of a plus I b into x minus of a minus I b, multiply it out, I would then get x squared minus of a plus I b plus a minus I b into x, and this is plus a squared plus b squared, that is x squared minus 2 a into x plus a square plus b squared, or I will write x squared plus p x plus q. Therefore, if I want to look at a complex pair which is of the form a plus minus I b, then the product corresponding to that pair is given by x square plus p x plus q, where p and q are real. So, in this product this 2a is real, a square plus b square is real. Therefore, if I want to extract a complex pair from a given polynomial, I would extract a real factor x square plus p x plus q. Therefore, this implies that it would be sufficient for me to extract a quadratic equation of the form. Therefore, we shall say to extract a complex pair, extract a quadratic factor x squared plus p x plus q from p n x is equal to 0. If I want to extract this complex pair, I shall extract a quadratic factor of the form x square plus p x plus q from p n x is equal to 0. Now, it is possible that I can extract a quadratic factor and it can give us a real pair also. It is not necessary, because when I try to extract x square plus p x plus q, I do not know at initially whether I am extracting a complex pair or a real pair. So, it is possible therefore to get a pair of roots also, real roots also from this. Therefore, this can also give a pair of real roots. Now if I take this polynomial p n x, we take the polynomial p n x, let us say the degree of this is even. So let us take degree is even, that is your n is even. Then if I extract the quadratic factor x square plus p x plus q, deflate it, I again extract x square plus p x plus q. Therefore at the end we will be left out with a quadratic factor, because n is even. So each time I extract the quadratic factor, so what will be left out in the end will be a quadratic factor. So I will be able to get reduce it into finally into a quadratic factor and find the two roots of this. Now when I extract a quadratic factor, I will use the usual rule of finding the roots of this quadratic, the rules of ordinary rule of this as minus p plus minus p square minus 4ac by 2, and then find out those roots. Whereas if p n x is degree is odd, if n is odd, then when I extract this quadratic factor x square plus p x plus q, then I deflate it and continue the process, I will be left out in the end a linear polynomial. Therefore I will be left out with a factor of the form some x minus a will be left out in the end, because it is an odd degree polynomial. We will have a discussion on this little later as to whether we should have a even polynomials considered only or odd polynomials can be considered. We will have a discussion on this later. Now the first method that we shall discuss is what is known as the Berge-Vitta method, which extracts a linear factor from a given polynomial. So we shall call this as the method as Berge-Vitta method. What this method does is it extracts a linear factor, extracts a factor of the form x minus p from p n x is equal to 0. So in this method we will try to extract a factor of the form x minus p from p n x is equal to 0, and the procedure or the method would automatically give us the deflated polynomial also. Now the Berge-Vitta method is nothing but the implementation of Newton-Raphson method to polynomial equations using synthetic division. Now we will define how we are going to about synthetic division, but the Berge-Vitta method is a implementation of the Newton-Raphson method. It is implementation of Newton-Raphson method, which we have done earlier for f x is equal to 0. So it is the implementation of Newton-Raphson method using synthetic division. Now if x minus p is an exact factor has been determined, let us suppose x minus p is exact factor, then p n x is divisible by x minus p exactly. So p n minus will be simply a polynomial of degree n minus 1 x. So this will be a polynomial of degree n minus 1. If x minus p is not an exact factor, if I divide by x minus p, what I would get here is a polynomial at degree n minus 1 plus a constant that will be a remainder. So let us now take the case x minus p is not exact, it is not a exact factor. Then p n x can be written as x minus p into q n minus 1 x plus r, where r we will call it as a remainder or is a remainder. Obviously r is identically 0 if x minus once it becomes an exact factor. So r will be identically 0 if x minus p is exact. Is exact factor. Now, it is this particular equation that I would like to use in order to implement the Newton-Raphson method by synthetic division. Now, let us open it up and write the entire thing here. First of all, we will see that as the factor x minus p which is not exact or the value p changes, in Newton-Raphson method we start with an initial approximation. So, if an initial approximation p is taken and every time change, remainder is going to change. So, as pk approximations tend to exact solution xi, r is going to go to 0. Initially remainder will be large. Now, as p tends to xi, which is let us call it as exact root, r tends to 0, r is the remainder. So, when once this p becomes exact root, r will become 0, r tends to 0. In other words, what we are stating here is that r is a function of p. As p changes, r changes, therefore remainder also changes. Therefore, r is a function of p, and therefore this is a nonlinear function of p. The problem therefore is to find a p such that r of p is 0, that is the remainder should be 0. So, the problem is to find p such that r of p is equal to 0. Now, before we write down the value of this, that is Newton-Raphson method, let us go to one step behind and let us just look at the particular equation that we have written here, this p n x is equal to x minus p q n minus 1 x plus r. Let us just write this particular equation again. So, I will write this equation as a naught a 1 x to the power of n minus 1 plus a 2 x to the power of n minus 2 a n minus 1 into x plus a n is x minus p yes, a naught x to the power of n, yes, x minus p b naught x to the power of, this is a polynomial q n minus 1 is a polynomial of degree n minus 1, therefore b naught x to the power of n minus 1 plus b 1 x to the power of n minus 2 plus so on b n minus 2 x plus b n minus 1 plus r. Now, I would like to use the Newton-Raphson method to find the value of this p. Now, before we do that, let us show a procedure which we call as the synthetic division procedure, wherein I can determine the coefficients b naught, b 1, b n minus 2, b n minus 1 and r from a naught, a 1, a 2 in a simple procedure. To do that, let us multiply the right hand side. The right hand side multiplication would give us b naught x to the power of n, collect the coefficients b 1, that is the coefficient of x to the power of n minus 1, the product of these two, minus p b naught x to the power of n minus 1. Then I take the next coefficient, x into next coefficient is b 2 minus p into b 1, that is p into b 1 x to the power of n minus 2. Then I take the general coefficient x to the power of n minus k. So, that will give me b k, that is x into b k x to the power of n minus k minus p b k minus 1, that is minus p into the previous coefficient, this is x to the power of n minus k plus so on. The last term would be, the constant term will be r from here and minus p b n minus 1. So, the constant will be r minus p into b b n minus 1. Now, what I do is I compare both sides of this particular equation, then I have here b naught will be equal to a naught, b 1 minus p b naught is a 1, so let us compare the both sides. Now, we compare the powers of x on both sides. Therefore, what I would get here is, from this I would get b 0 is equal to a 0. So, b 0 is equal to a 0. Then I get b 1 minus p b 0 is equal to a 1, that is b 1 minus p b 0 coefficient of x to the power of n minus 1 is equal to a 1. Therefore, I get b 1 is equal to a 1 plus p b 0. So, I solve from here for b 1, that is a 1 is plus p b 0. Then I go to the next coefficient, that is our b 2 minus p b 1. So, I will get b 2 minus p b 1 is equal to a 2. So, that is my a 2. I solve for b 2 again, b 2 is equal to a 2 plus p into b 1. So, I take it to this side. Now, I compare the general term b k minus, I will compare the general term b k minus p b k minus 1, and that is equal to a k. Therefore, I can solve for b k from here as a k plus p times b k minus 1. Then I go to the last term, the constant term r minus p b n minus 1, r minus p b n minus 1 is equal to the constant coefficient, that is a n. Therefore, from here I get r is equal to a n plus p b n minus 1. We can see that the entire set of equations can be given by single recurrence relation out of this set, and that recurrence relation is this recurrence relation, and where I define b n as r. So, let us just denote r as b n, let us denote r as b n. Then I can get all these term coefficient b 1 b 2 from the recurrence relation. I can now define a recurrence relation b k is equal to a k plus p b k minus 1, and k going from 0, 1, 2, 3 n. Of which the first and last coefficients are to be defined. We have b 0 is equal to a 0, b 0 is equal to a 0 is defined from this top, and b n is equal to r is equal to b n. So, b n is equal to r. Now, every coefficient b I can be obtained from a I by this simple recurrence relation. Now, we will just put it in a F format, which I shall call it as synthetic division. I will write it. Let us write down what is our Newton-Raphson method. The Newton-Raphson method is, let us write down the Newton-Raphson method for the finding this particular root is p n plus 1 is equal to p n minus p n of p k, let us put p k by p n prime of p k. So, this is our Newton-Raphson method. Now, in this I need the values of the polynomial at p k, the value of the derivative of the polynomial at p k. Now, what I would do from here, I would get the value of the derivatives also using the same recurrence relation, but in a different format. Now, first of all, if you let us just go back one sheet earlier. If you look at this particular starting point of p n x is equal to x minus p q n minus 1 of x here, at any particular stage, if I put x is equal to that particular approximation p k here, this term goes off and I will get r. Therefore, p n at a p k is equal to r. So, if I substitute it here in this one, or let us write down again here, what we have here is p n of x is x minus at any particular stage, this is the equation n minus 1 x plus r. So, as the approximation initial approximation changes, this is the the first equation looks like. Now, when I substitute x is equal to pk here, what I would get here is Pn of pk is equal to r. This term cancels, I will get r. So, what we are stating here is that the numerator in the Newton-Raphson method Pn of xk would be nothing but r, that is equal to Bn. So, here we have denoted r is equal to Bn, and therefore, Pn of pk is equal to r. Now, we are stating that r is equal to Bn. Therefore, in the recurrence relation that I have got, the last term of this that gives me Bn from this set, that last value itself will give me the value of the numerator Pn at pk. Now, I want the denominator, that Pn prime of pk. Now, to get this, it is a very simple and interesting procedure. I would take 1 and differentiate this with respect to p. So, what I would do is differentiate the equation 1 with respect to p. Then it will simply dbk by upon dp is ak is independent of p, therefore, that is 0 plus product of these two terms. So, let us differentiate it, bk minus 1 plus p dbk minus 1 upon dp. So, I have differentiated this product to get this particular quantity here. Now, we will use a notation now to simplify this. What I would do, I would say denote dbk upon dp, this quantity as c k minus 1. It is just a notation, there is no special meaning about it, we are just denoting dbk is equal to c k minus 1. If I do this, then this equation will look like this is c k minus 1, put k is equal to k minus 1, this will be c k minus 2. Therefore, this equation can be written as c k minus 1 is equal to b k minus 1 plus p times c k minus 2. So, this equation can be rewritten in the form of c k minus 1 is equal to b k minus 1 plus c k minus 2. Now, if I put k is equal to k plus 1, I could rewrite this as simply c k is equal to b k plus p c k minus 1, where we have to define the first coefficient. Let us define what is C0. If you look at C0, when you take k is equal to 1 here, that is your C0, that will be db1 by dp. So, this is by definition db1 upon dp. And let us go backward one step and see what is our b1. b1 was a1 plus pb naught. So, we will substitute for that, that is equal to d upon dp of a1 plus p b0. And therefore, this is equal to this, what is this? This will be simply equal to, this is 0 plus b0 plus 0, therefore, this is equal to b0. b0 is equal to a0. So, if you look at that, just b0 is equal to a0, therefore, derivative with respect to p will be 0. Therefore, after this product only b0 will survive and everything else will go. Therefore, c0 is defined as b0, and the previous step b0 is also defined as a0. Now, with this reconciliation, now I can set k is equal to 1 to up to n minus 1. Now, what we were asking for here is, I need the let us just go back here, I need the derivative Pn prime of at pk. So, let us write down what is dPn upon dP. So, that is what I need in the denominator Pn prime of Pk, that is dPn upon dP. But we have shown earlier that Pn of Pk is equal to R. Therefore, this is equal to dR upon dP. We have shown from this Pn of P is equal to R. So, this is of course at Pk, we are talking at a approximation Pk. dR upon dP means we have shown R is equal to Bn. So, this will be dBn upon dP. And let us go to the definition of the C. So, if I set here n, k is equal to n, this is Cn minus 1. Therefore, this is equal to Cn minus 1, this will be equal to Cn minus 1. Now, what we are therefore stating is, in this recurrence relation, the last coefficient here we are going only up to n minus 1, the last coefficient Ck, when k is n minus 1, Cn minus 1 will give me the derivative of Pn. Therefore, the numerator is given by the last coefficient in this, last coefficient in the previous set recurrence relation, and the last coefficient in this recurrence relation gives me the derivative. This is what is required for the new application Newton-Raphson method. But if you look at the two recurrence relations, if you just look at the two recurrence relations, this is your Bk is equal to Ak plus Bbk minus 1, Ck is equal to Bk plus Pck minus 1, both are identically the same except B is replaced by C, A is replaced by B. In other words, the procedure that I use for getting Bk from Ak is identically same as how we derive C from B. That means, as I proceed on with the synthetic division, if I obtain Bk from Ak's, I can then obtain from Ck by identical procedure from Bk. Now, let us see what I mean by synthetic procedure, how we can get computationally a very simple procedure to obtain all these coefficients, and the application of the Newton-Raphson method therefore becomes extremely simple for polynomial equations. Now, let us write this in what is known as the synthetic division procedure. So, what I would do here is, I would write down all the coefficients of the polynomial in the order. So, I will write down all the coefficients a naught, a1, a2, so on, a n minus 2, a n minus 1, a n. Then I will take the root I am extracting p is the approximate root, I am writing this one. So, let us put a line like this. Now, I will on this line I will get my values of b's, all my b's will come here. So, let us just look at this and go about this one. Let me put this sequence here. B0 is A0. So, there is no change in B0. Now, multiply P with B naught and put it here. B1 is equal to A1 plus PB naught. So, multiply PB naught here. So, I will insert this P into B naught, the current B that is available to me. Add these two, that will give me B1. A1 plus PB naught is equal to B1. Now, multiply B with the current B1 is available, that is your P B1. I get P into B1. Add these two, I will get B2. Now, we proceed on like this. At this moment, I have got here P into Bn minus 3 is available to me. I will get here Bn minus 2, then P into Bn minus 2 will give me Bn minus 1, P into Bn minus 1 will give me Bn. Now, we have just now proved that Bn is equal to Pn Pk, that is equal to R. That means, the last coefficient that I have got here is R. This last coefficient in this one is given R. Now you can see when you are doing with on a calculator these computations for this, you have started with a B naught multiplied by P naught A1, what is currently available on your screen is P1, multiply by P, add A2, what is currently available to you on the screen is B2. So all these coefficients will be so trivially done on the calculator without doing any, I mean the way in which that you normally delete the number, write it again. We are not doing it. When once start the procedure, whatever is available in the screen is currently available data for you to manipulate on. So PB1, add it, A2, you have got a B2, multiply by B2, add this number, I get B3. So you get just compute and then finally land into Bn, and this turns out to be the value of the numerator or Pn at Pk. Now we said that the next division, synthetic division, will give me Ck, but Ck will be obtained exactly in the same way as we obtained from Bk. So just as we obtained in the Bk from Ak, I can now obtain Ck from Bk. That means I should continue this procedure one more step down. So I can now write down again P, I write down or rather I need not write P here, I can assume that P is available to me here. Now we are shown C0 is P0, so it will again C0 is P0. There is no change. When once you have defined here your C0 is equal to B0, then C1 will be B1 plus PC naught. Therefore the same procedure that will be obtained over here. Oh sorry, I should start with C naught, let us take C naught, C naught. So this will be my C1. I multiply this P with C1, so I am multiplying P with C1, so I add, I will get C2. I do go on doing it, this will be PCn minus 3 will give me Cn minus 2, and I multiply this by PCn minus 2, I will get here Cn minus 1. Now we have shown in the previous step that our derivative is simply Cn minus 1. Therefore this last coefficient is your dr upon dp. So this last coefficient is our dr upon dp. Now you can see that these coefficients are obtained from this just as we have done the previous step, and we are not. This procedure is called the synthetic division. So this is called the synthetic division. It is something like the Horner's process for evaluating a polynomial. As I mentioned earlier, the worst way of evaluating a polynomial is to substitute the value in it and take all the powers and write it. Suppose you want to get a polynomial degree 20, x to the power of 20 plus coefficient in x to the power of 19, and you want to get the value of this as 1.5653. Now if you substitute it here, take the 20th degree of this, substitute there 19th degree and this, that is the worst way of evaluating a polynomial, because the maximum possible round off error would be there in such an evaluation. The best way of evaluating polynomial is the nested looping of the Horner's procedure. So this is almost the same as that particular procedure which we are doing it. In fact if you open it from backwards, we are now multiplying by the previous quotient. So it is like a loop we are doing it. It is similar to a Horner's procedure of evaluating a polynomial, and this is the best way of evaluating a polynomial, and this is called the synthetic division procedure. The interesting that you will notice here that this coefficient turned out to be value of the function at Pk, this turned out the value of the first derivative at Pk. Now the question comes, can I find the second derivative, third derivative from here if you want it? The answer is yes. Just proceed the synthetic division procedure one more step, I get d, I can write down dk is equal to ck plus p dk ck dk minus 1. So I can write down a new relation like dk is equal to ck plus p dk minus 1. I would stop at one more less, here it is n, I stopped at n minus 1, I will stop at n minus 2. Then this your dn minus 2 would be interestingly 1 upon factorial 2 of d square r upon dp square. This will be 1 upon factorial 2 of d square upon dp square. Therefore I can find any derivative of the given polynomial by continuing this synthetic procedure until the, except that we will have here factorials here. Now when once these two values are obtained, I will now substitute in the Newton-Raphson method that we have. So, let us write it again. So, with these values that is available for us, I will now do P k plus 1 is equal to P k minus B n by C n minus 1. Now, this is the next iteration that has been obtained. Let us, for each value of P k we are doing synthetic division procedure once and then computing, we plot each iteration. So, we are doing iterations. Now, let us assume that the root has been found. Let us say that some P n is approximately xi. So, to the degree accuracy, to the accuracy which you have to the accuracy. So, that means you wanted 6 decimal place of accuracy. So, you have computed the number of iterations using the that many iterations to get the to the root approximating the exact root. Then I want the deflated polynomial, so that I can go to the next step. Now, if you look at the first step of the procedure that we have written here, I will just go back to this, just go back and have a look at this one. If I have obtained the root to the required accuracy, then R is approximately 0. So, this implies that R is approximately 0, because we obtained the required accuracy. Now, when R is approximately 0, this itself is the deflated polynomial, because I am dividing this by x minus p, what is left out is the deflated polynomial. Therefore, this implies that whatever I am getting q n minus 1 x in that synthetic diffusion is the deflated polynomial, Now, what we would therefore say is, when once you have got your required solution to the accuracy, do the synthetic division procedure only the first step of it. So, we will say use the first step of synthetic division procedure, after finding P n to determine q n minus 1 of x. So, we would repeat this procedure of synthetic division that we have done here. This synthetic division procedure, one step of it we will do and then stop it and then pick that as my polynomial q n minus 1, which is a deflated polynomial. Now, I will obtain the next root if it is required to apply it on q n minus 1. Therefore, as we proceed, the degree of the polynomial will go down each time by 1. So, if you have started with the polynomial degree 20, you have extracted to the root 6 multiplices. Now, I have a polynomial of degree 19. Now, again I extract the next root, then it goes on reducing. Now, one very important thing that happens here is that the root that has been extracted, that means it has been removed. Therefore, there is no chance that when you write an approximation to the next root, it is going to go back to the original root. As we mentioned earlier, if suppose you are using p n x itself and you are using the next root again, there is a possibility if the roots are sufficiently close, you may be going again to the root that has already been determined. Now, therefore, once you extract it or remove it from that particular root, there is no chance that the root will again go back to the original root. So, that is the advantage. Now, let us take an example on this. So, let us take this example. Let us find the smallest positive root. X 4 minus 3 x cubed plus 3 x squared minus 3 x plus 2, let us say using Berger-Vitta method. Okay, let us take the fix up the smallest positive root is required. So, I would consider what is my f of 0, that is equal to 2, f of 1 is 1 minus 3 plus 3 minus 3 plus 2. Right, for this the root turns out to be 1, is not it. So, this is equal to that comes out to be 0. So, the root as 0. Let us take an approximate value and then let us take the root as p0 is equal to some 0.5 and then try to extract the root from this one. Let me take the next this one. So, let us write down the coefficients. The coefficients are 1, minus 3, 3, minus 3, 2. So, we take this p here, I will write this as p is 0.05. This is your b naught, that is 1, multiply these two, I will get here 0.5, sum them up, minus 2.5, 0.5 into 1.25 minus 0.25, that is minus 1.25, sum them up, I will get 1.75, 0.5 into this is 0.875, add the 2, 2.125, add this 2, now multiply by 0.5, that is minus 1.0625, add up, I will get here 9375 and that is equal to B4. B naught, B1, B2, B3, B4, this is B naught, B1, B2, B3, B4. Then I need one more step, 1, that is C naught is equal to B naught, 1 into 0.5, that is minus 2, that is equal to 1, 0.5 into minus 2, that is minus 1, that is equal to 0.75, you multiply by 0.5, I will get has 3.75 minus 1.750, that is equal to C3. Now, first iteration is complete. I will now find out what is my P1. P1 is equal to P naught minus B4 by C3. So, we can substitute the value 0.5 minus 0.9375 by minus 1.750. I will give you the value of this value is 0.0356. Now, the first iteration is complete. Now, I will repeat this synthetic division procedure using this particular value. So, let us do that one. So, let us again write this here as 1.0356 here and then write down these coefficients 1 minus 3, 3 minus 3 and 2. I have 1 here, multiply 1.0356. I will give the values of this if it is slightly difficult for you to do this. So, this is minus 1.9644. Now, I multiply these two and put it over here, I will get a minus 2.0343, that is this product and sum them up, I will get a 0.9695 and 7, 9657. Now, I am multiplying this and putting it here, it comes out to 1.001 minus 1.999. I multiply these two and put it here minus 0.711 and this is minus 0.711, that is equal to your B4. Indeed, this B4 is an indicator for us whether the solution is good enough or not. Now, let us proceed with the next step. I have 1 here, multiply this 1.0356, therefore, this gives us minus 9288. I multiply these two minus 0.9619 and this gives me 0038 and finally, I have this as 0039 minus 1.9960. Now, the values B4 C3 is available. I can go compute my next iteration, that is P2 is equal to P1 minus B4 upon C3 and that is P1 is 1 point, it is here P1 is here 0356 minus 0.711 divided by minus 1960 and this value is 0.99979. So, it is approximately 1. Now, we have extracted this root, this is the approximation of the required accuracy, we extracted the root. Now, I want the deflated polynomial. To get the deflated polynomial, I must use the last approximation and do the first step of the synthetic division procedure. So, let us do it. So, I now take this 1 as the root and then write down the coefficients 1 minus 3, 3 minus 3, 2 and this. So, I have 1 here minus 2, this is minus 2, 1, 1 minus 2. Now, I want to compute this because I do not need it. Here it turns out to be that is 0 because that is turned out to be an exact solution. So, if you just try to write down what this is 0, this is your B4 because that happened because it turned out to be the exact solution problem. Now, this coefficient, these should be give me my q n minus 1x. Therefore, the polynomial of degree q3, the deflated polynomial is b0 x cubed plus b1 x squared plus b2 x plus b3. So, that is our b0 x cubed, b1 x squared, b2 x plus b3, that is x cubed minus 2 x squared plus x minus 2. Therefore, we have now obtained the next lower factor, that is x cubed minus 2 x square plus x minus 2. Now, if I want the next root, I will now apply the Newton-Raphson method on this deflated polynomial. So, therefore, in the synthetic division procedure, your deflated polynomial is automatically available for us in the first step itself. Now, I think we would stop at this. In the next time, what we would do here, this procedure is possible only if we are finding the real roots. If this is a complex root, then it is a complex pair. So, I will not be able to use this extract a single factor from a given polynomial to extract a complex root. Now, if I want the complex root, the only way is that I have to extract a pair. If I extract a pair as x square plus px plus q, then I can extract the complex pair as well as a real pair of equations also. Okay, we will stop at this.